I am Dr. M. Amuda, Associate Professor of Chemistry, V. Vanniyaperumal College for Women, Virudhunagar. In this video, we are going to discuss about the inorganic chemistry coordination complex compounds crystal field theory. Features of crystal field theory: splitting of d orbitals, spectrochemical series, high spin and low spin complexes, magnetic properties of complexes. Under this heading, we are going to discuss. Then, in coordination chemistry, in D block elements, in 3D series, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc element complexes are in different colors. What is the reason for that colors? First of all, we should know the electronic arrangements in d orbitals. In scandium, 3d1 4s2, titanium 3d2 4s2, vanadium 3d3, chromium 3d5, manganese again 3d5, iron 3d6, cobalt 3d7, nickel 3d8, copper 3d10, zinc 3d10. You see, scandium and zinc complex compounds are colorless. From titanium to manganese, the intensity of the color is increased. Then from iron to copper, again the intensity is decreased. What is the reason for that increase and decrease that intensity and colorless of these complex compounds? We will see in the next video. Then coordination compounds, we all know the arrangement of the electrons. In 3d orbital, there are 5 lobes. In d orbital, there are 5 lobes. First one, x squared, d x squared minus y squared, dxy, dyz and dz squared. In octahedral geometry, let us consider the metal complex is located in the crystal. In that crystal field, dx squared and dx squared minus y squared are Eg orbital, then dxy, yz and xz are considered as the T2g orbital. That means triply degenerate, Eg means doubly degenerate. These orbitals are located along the Cartesian of the octahedral geometry. Then in between the Cartesian of the that octahedral geometry. Here dz squared and dx squared minus y squared are located along the geometry. Then dxy, yz and xz are located in between the geometry of the octahedral complexes. Here copper, when it reacts with water molecule, we can get the aqua copper 2 complex. When this complex is react with ammonia, we can get the much intense blue color complexes. Here in this complex compound, cobalt is the central metal ion, ammonia is considered as a ligand. Then this is the coordination complex. Coordination number of cobalt compound is 1, 2, 3, 4, 5, 6. So octahedral complex, ammonia is considered as a ligand, cobalt is a metal compound. Here copper is a metal compound, 6 ligands are aqua, then water molecule is replaced by ammonia ligand. Metal is considered as a central metal ion, then the molecule which are react with that central metal are called as ligands. So here mixed ligands are reacted with copper and form a different complexes. 4 ammonia molecule, 2 water molecule. Here 6 water molecules are completely reacted with copper molecule and get the blue color. Here these ammonia and 2 water molecule are mixed ligands. Another example, hexa aqua ferrate 3 ion. Here 6 water molecules are ligands. These ligands are called as aqua these ligands react with iron molecule, that means iron atom, and give the pale violet color. After the reaction of thiocyanato complex ligand, then it form a red colored mixed ligand complex. Okay, what's the reason for that color change and the magnetic property? These things are discussed in this crystal field theory. Here, this is the central metal atom. This d orbital is present in the metal ion. dxz, dyz, dx squared minus y squared, dxz are the 5 lobes of metal atom. This is the carbonyl ligand. In the carbonyl ligand, some lobes are there which also possess the electrons. These metallic lobes as well as the ligand lobes are mixed together and form a complex compound. This is the mechanism behind that reaction. Then what are the hypothetical points which are discussed in the crystal field theory? Ligands, that means ammonia, aqua, cyanide, thiocyanato, are considered as a point charges. There is no bond formation between the metal and the ligands, just exchange of the electrons, that means electrostatic interaction is taking place. Here, oriented along the Cartesian axis, that means x squared minus y squared orbital as well as dz squared orbitals are oriented along the Cartesian axis. Then, in between the Cartesian axis means in octahedral complexes, dxy, yz, xz, these 3 orbital lobes are located in between the Cartesian axis of the octahedral complexes. That means there is no sharing of electrons in between the ligands and the central metal atom, just the electrostatic interaction is attained in that complex compound formation. Here there are 2 types of ligands: cyanide ligand, thiocyanato ligand, carbonyl ligand, ammonia ligand, EDTA, ethylene diamine. These ligands are considered as a strong field ligand because when these ligands approach the central metal atom, these 5 lobes, there are 2 types of lobes, T2G lobes, EG lobes. These T2G and EG lobes, dxy, dyz, dxz, these 3 are triply degenerate T2G orbitals. Here, dx squared minus y squared, dz squared, these 2 are doubly degenerate orbitals. When the metal atom in the ground state, all the 5 orbitals are in the same energy level. There is no dissipation of energy among these 5 orbitals. When the ligand approaches, whether it is strong field or weak field ligands, when the ligand approaches the metal atom, these 5 lobes of d orbitals doubly degenerate. That means T2G and EG. T2G orbitals release the energy and comes down at the ground level. Then EG orbital, that means x squared minus y squared and z squared lobe of that orbital gains the energy and goes upward from the ground state. That means plus 0.6 energy is gained by these 2 orbitals, minus 0.4 del octahedral energy is released by these 3 T2G orbitals and goes down from the ground state. At that time, some energy gap, that means octahedral energy, this is the crystal field stabilization energy, is this energy gap is formed in the metal ion. Cyanide, carbonyl, nitrate are the strong field ligands. This is the dxy orbital, that means this red color denotes the orbital of the metal atom, blue color denotes the orbital of the ligand. When this electrostatic interaction carried out, some energy is increased. That means some energy is gained by this molecule and the energy gap is increased between the T2G and Eg. Here iodide, chloride, fluoride, bromide, these all are weak field ligands. When these ligands approaches the metal ion, the d lobe orbitals decrease the energy level and the energy difference, that means energy gap between the T2G and Eg orbital is less. Here hexafluorocobaltate, here hexacarbonyl ferrate. Fluoride is a weak ligand, carbonyl is a strong ligand. T2G Eg gap is decreased. Here T2G Eg gap is increased due to the presence of the weak ligand. Here the presence of the strong ligand in the metal atom. You see, here is the Fe2 plus d orbital which is present in the ground state. D6 orbital, here 1, 2, 3, 4, 5 again starts to fill the first orbital paired. According to Ohm's rule, pairing is started. Here when water molecule aqua ligand, this is the weak ligand. When iron is react with aqua molecule and form a hexa aqua ferrate 2 ion, this is the complex compound, this is central metal ion, this is weak ligand. Here the same iron atom, cyanide is a strong ligand, hexacyanoferrate 3, this is the strong ligand, this one is weak ligand. When weak ligand approaches the metal ion, T2G Eg, these two are Eg, these three are T2G. The gap between these T2G and Eg is less when the weak ligand approaches the metal atom. At that time, the electrons are started to fill and form a unpaired structure. That means 1, 2, 3, 4, 5. Here unpaired means the electrons are singly filled. Here when strong ligand, cyanide is a strong ligand, when the strong ligand approaches the metal atom, here somewhat large energy gap is formed because during the back donation of that strong ligand with the metal atom, the energy gap between the T2G and Eg is increased. At that time there is no pairing, there is not possible for the filling of individual electron in Eg level because the pairing energy is less. So all the electrons, all the 6 electrons are started to fill in the lower energy level orbital, that means in T2G orbital. So paired electrons are formed. This is the reason for the paramagnetic and diamagnetic behavior of this magnetic complexes. That means magnetic property of these complexes are also explained by the crystal field theory. Here this is the paramagnetic. Paramagnetic means when this complex is located in the magnetic field, that magnetic flux is formed. When this complex is located in the magnetic field, there is no magnetic flux is formed because there is no unpaired electron in strong field ligand. Here paired electrons are there. These paired electrons mingled together and form a new magnetic field in the magnetic flux of that paramagnetic complexes. Here there is no formation of magnetic field because all the electrons are paired, plus half and minus half are equal to 0. That means all the magnetic behavior of the electrons are neutralized within themselves. So there is no possibility for the magnetic behavior of this strong field ligands. Then we are going to separate the ligands into 2 groups. First one, weak field ligands, then strong field ligands. When the strong field ligand increases, the magnetic behavior as well as the colored nature of individual complexes are differed. Chloride, halide compounds, that means iodide, bromide, chloride, fluoride, up to OH, all are considered as a weak field ligands. That means water molecule is neutral ligand. Sometimes it behaves as a strong ligand when it mixed with the weak field ligands. Sometimes it behaved as a strong field ligand when it compared with the strong field ligands. Then from ammonia to carbonyl compounds, strong field ligands are started. So when strong ligand, that means when strong field ligand interact with the metal atom, their magnetic properties as well as the coloring nature is differed. Then when weak field ligand interact with the metal atom, their magnetic property as well as the colored nature are different. So these all are the important features of the crystal field theory. Here you see, this is the iron compound, H2O molecule. Here ammonia, copper, ammonia. Iron, water molecule, this color is purple color. Here water, ammonia molecule is blue color. These are here mixed ligands are linked with the copper ion. Here same ligands, all the aqua molecules are linked with the iron atom. When the magnitude of octahedral, that means the separation energy depends on many factors. The nature of the 6 ligands located around the central metal ion. Sometimes same ligands are surrounded with the central metal ion. Sometimes weak field ligand as well as strong field ligands are mixed and located in the octahedral complexes. At that time, the magnetic property as well as the color of the individual complexes are differed. Then charge on the metal atom. In sometimes metal ion, for example, if iron atom is mixed with the strong field ligand, it carries 3+ state. Or else in weak field ligand, it may carry 2+. So +2 or +3 or +4 oxidation state may vary the color as well as the magnetic property of that individual compound. Whether the metal is using 3D or 4D, that means inner orbital octahedral complexes, or 5D, that means outer orbital octahedral complexes. That may differ the ligands produce different crystal field splitting nature. At that time, the stabilization energy, that means the stability of that complex may differ. The increasing crystal field splitting produced by ligands is expressed in spectrochemical series. Here, strong field ligands ammonia, weak field ligands is water. Magnetic behavior as well as the coloring nature is explained by the crystal field theory. Okay, here you see mixed ligands, same ligands are combined with the cobalt atom. So the nature of the ligands, then the splitting effect may vary, which depends upon the ligands. Okay, we will see the stabilization energy in the next video. Thank you.